Well, it's Valentine's Day, and there's nothing I'd rather discuss more than my one true love, or my four true loves, the four fundamental subspaces. So let's jump right in. All right, remember, if we're dealing with an m by n matrix, the null space consists of certain vectors that live in R to the number of columns, so that's Rn. So the way I like to visualize this is I think of the matrix as a machine from Rn to Rm, and I think of the null space as living inside of R to the n. On the other hand, the column space organizes certain vectors that live in R to the number of rows, and the column space also fits nicely into this picture. A transports vectors from Rn to Rm, so the column space lives on the right-hand side of this picture. Great. Now remember, if we transpose our matrix A, what we're really doing is we're constructing a new machine that doesn't go from Rn to Rm, but the other way around, because we're changing the rows and the columns. So there's nothing preventing us from looking at the null space and the column space of the transpose of our matrix. Well, if the null space of the original matrix lived inside of R to the number of columns, the null space of the transpose should live inside R to the number of rows. So the null space of the transpose lives alongside the column space. And if the column space of our original matrix lived inside of R to the number of rows, the column space of the transpose should live inside of R to the number of columns. So the column space of the transpose of our matrix lives alongside the null space of our matrix. So these four subspaces are what we call the four fundamental subspaces of a matrix. We have the null space of our original matrix, which lives alongside the column space of the transpose, and both of those are inside of R to the number of columns. And we have the column space of our matrix, which lives alongside the null space of the transpose inside of R to the number of rows. And remember what the various tests are. So if we want to check whether or not a specific vector lives inside of the null space of a matrix, all we have to do is take the vector v, multiply by a, and check whether or not we get the zero vector. On the other hand, if we want to check whether or not a vector lives inside of the column space of a matrix, the task is a little bit more involved because it involves row reductions. The Roche-Capelli theorem essentially tells us that we should check the equation rank of A equals the rank of A augmented with V. So we augment A with V, and we do the row reductions, and we look whether or not there's a pivot in the augmented column. If there is a pivot, that means V is not in the column space, and if there's no pivot in the augmented column, that means V is in the column space. And of course, the tests work for the null space of the transpose in the column space of the transpose, except we just have to transpose A before we apply these tests. So if you want to check whether or not a vector V is in the null space of A transpose, we take A transpose and multiply by V and check whether or not we get the zero vector. And if we want to check whether or not V is in the column space of the transpose, we should augment the transpose of A with V and do our row reductions to check whether or not there's a pivot in the augmented column. So I love this picture because there's so much information being very elegantly presented here. So whenever I'm working on a problem involving a matrix, I always write this picture down. Now, there's some terminology that we'll be using, and I want to justify the terminology. So ask yourself, what does it mean to say that a vector is in the null space of the transpose? Well, what that means is that if we transpose A and multiply by V, we produce the zero vector. Now what I'm going to do is I'm going to transpose this whole equation. So I'm going to transpose A transpose times V, and I'm going to transpose the zero vector. Now, there's nothing interesting to say on the right-hand side of this equal sign, but there is something interesting we could do on the left-hand side. Remember, transposition is order reversing. So I can distribute this transpose, but I have to reverse the order of A transpose and V. So let's do that. So this becomes V transpose multiplied by A transpose transpose. But of course, if we transpose twice, we get back the original thing. So the equation that defines whether or not a vector is in the null space of the transpose of our matrix can be interpreted as the transpose of the vector multiplied by A on the right equals the transpose of the 0 vector. And it's for this reason that the null space of the transpose of a matrix is often referred to as the left null space of A. So if you want to check whether or not a vector is in the null space of A, you multiply on the right and see if you get the 0 vector. If you want to see whether or not a vector is in the null space of the transpose, our procedure here shows that what you could do is you could multiply on the left by V transpose and check if that produces the transpose of the 0 vector. Of course, this is the exact same thing as saying A transpose times V equals the 0 vector. So this justifies the terminology left null space. What about the column space of the transpose? Well, remember that the column space of a matrix consists of all linear combinations of the columns of that matrix. Therefore, the column space of A transpose consists of all linear combinations of the columns of A transpose. A more mathematical way to write this is to say that the column space of A transpose is equal to the span of the columns of A transpose. But remember, the columns of A transpose are the rows of the original matrix. So this is the same thing as the span of the rows of the original matrix. So the column space of A transpose consists of all linear combinations of the rows of A. And it's for this reason that the column space of A transpose is often called the row space of A. So now with this terminology, we can describe, or we can name all four of these fundamental subspaces. So for an m by n matrix, we can view it as a machine that transports vectors in R to the number of columns into vectors coming from R to the number of rows. The null space lives alongside the column space of the transpose inside of R to the number of columns, and we just call the null space the null space. On the other side, the column space lives alongside the null space of the transpose, and we just call the column space the column space. But because of the calculation we did a moment ago, we call the null space of the transpose the left null space, and because of the other observation we just made, we call the column space of the transpose the row space of the matrix. So here we have a complete picture of all four fundamental subspaces of a matrix, and we have terminology to refer to each one individually.